let's talk about current, the flow of electricity, the flow of charges. Here I've got a simple parallel circuit. I've got a 12-volt battery attached to an 8-ohm resistor and another 8-ohm resistor in parallel. They each have their own path to the battery, which means that this one doesn't care what this one's doing. This one says, I have my own path to the battery, great. And this one says, I have my own path to the battery, great. Okay, so think about the current. So what is current? We have current in amps. And what the current actually is really it's a measure of how many electrons are going by per second at its basic level. So it's the number of charges going by a certain point in a certain amount of time. Which means if we take the measurement of the current right here, let's call it I1, we are told, okay, let's say it's, I don't know, 3.6 amps. That is a measure of how many electrons go by per second. There's, some unit fussing, but basically, yeah, it's a measure. Now, all the electrons that are going to come here, and then they get to this point. What are they going to do when they get to that point? You probably have a really good answer for that. Well, some are going to go here, some are going to go here. Yes. How much are going to go down this side, and how much are going to go down this side? Well, if we have equal resistances, equal resistors, the two paths are going to be equally hard for charges to flow through, and so we would have 1.8 amps and 1.8 amps. And we know it has to add up to 3.6 because you can't create or destroy charge. We can't have more electrons per second leaving this junction than entered. If 32,000 entered in 1 second, 32,000 had better leave in 1 second. And so at this junction, we know that all of the currents that go into a junction must be the same as all of the current that's coming out of a junction. And we can also talk about what happens if we have different resistances. Let's say we've got a 12 ohm resistor here and a 24 ohm resistor here. Resistors are a resistance to the flow of charges. So if we have a certain number of electrons coming through here, how many are going to go this path? How many are going to go this path? See if you can think through, reason through what is going to happen to the amount of charge flowing here, the amount of charge flowing here. You can, the math isn't too bad if you just say, I think it's going to be this ratio or whatever. Give it a try. All right, so I have a 12 ohm resistor here, 24 ohm. Which path is harder for charge to flow through? The more resistant one. So this path is more resistant to charge flowing through. That means that this one's easy. We're going to have more electrons flowing through the easier path, fewer electrons flowing through the harder path. And if the harder path is twice as resistant, well, it should get half the current that the other one does. So this, the current coming through this branch should be half of the current coming through this branch. So hard path, half the current of the easier path. So to break that up, it's not halves, you got to do thirds. And so what we end up with here is we're going to have a total of 3.6 amps. We're going to have 2.4 amps coming here. Oh no, did I do it wrong? I did it wrong. 36 divided by 3 is 12. So I need, yeah, I almost had it right, 2.4 and 1.2. I can do math. So we have a total coming out of 3.6 because we know we can't create or destroy charge, and so the total going into the junction has to be the same as what's going out. And then we also know that this harder path should have half the flow of charge that this one does. Makes sense, right? And so this idea is, it's actually a couple ideas. We're dealing with Ohm's law and the idea that if we have more resistance, we're going to have less current. We also are talking about the conservation of charge at a junction. If I were to make another loop, I'm just going to get rid of all of that. Oops, let's keep that. If I were to say, all right, I'm going to add yet another resistor into this, and we'd have 3 coming out, because the battery is just pushing charge, boop, boop, boop. We'd have 3 coming out. If I had 3.6 amps here, I don't want to do the math, but this plus this would have to equal 3.6. And that's just the idea of conservation of charge, but it's also known as Kirchoff's junction rule. And the junction rule is pretty easy. All of the current going into a junction must equal all of the current that comes out of a junction. So add up all the current entering a junction, that has to be equal to all the current, adding up all the current that comes out. Conservation of charge. So there is just a basic rundown on current and Kirchoff's junction rule.